Who doesn't know me?
Who doesn't know you? Hands. First liar, then second liar. Okay.
For the many people at home.
For the millions. Okay. The most important point in his career was that he finished his PhD in Vienna. Anyway, he's now in Geneva working with Nicolas on a topic that raised some interest also for people from relativistic quantum information. I'm sure there will be a lot of discussion, so I don't take too much time. The stage is yours.
Thank you, Czesław. Thank you all for being here. Good morning. Yeah, so today I'm going to talk about this new work I've been carrying out with Nicolas Gisin in Geneva, and the topic is this topic that came back into fashion recently in the quantum field theory community and to some extent in the relativistic quantum information community, of what is called the impossible measurements. Which, if you're not familiar with, I will define in a moment. So the first thing I want to stress from the outset is that our empirical sciences are successful because we are able to inquire nature. We can ask questions to nature. And if the dialogue wants to be a bit not boring, we also would like to have answers for nature. And this comes in the form of measurements. And to get an answer, measurements must have an outcome. This seems straightforward, but there is a big community, a big debate, and many parts in the literature where measurements do not bear outcome. So I will take as granted that a measurement is defined by something that gives you back a classical outcome. Now, measurements in quantum mechanics, as we all know, come with quite a baggage of problems. There is the notorious measurement problem of course, what breaks these, how do you put together this appearance of outcomes with certain probabilities and the unitary description of quantum physics, but today I'm not going in that problem. Rather, I would consider a second class of problems for quantum measurements, which I call here the possibility of measuring problem. Namely, we have a certain, in a theoretical framework in quantum physics in this case, we have theoretically acceptable measurements that are well defined. However, are all the measurements that are well defined by the theory physically acceptable, physically possible? Namely, without violating some fundamental principle within the same theory or with other successful theory that we believe are empirically adequate. And this brings me to such a class of problem, which is Sorkin's impossible measurements. So Raphael Sorkin in 1993-94, he devised this kind of scenario. So all of this was carried out in quantum field theory formalism, and so far mostly discussed only in the quantum field theory community, with the exception a bit of some relativistic quantum information. But let me focus on the original one. So the scenario is the following. You have a certain region of space-time that I denote with S, stands for sender, and another region of space-time which I denote by R, receiver. And these two regions are space-like. So there is space-like separation between the two. This is a Minkowski graph. So imagine that these are the forward light cone and the past light cone, respectively, of S and R. So you see that these two regions being space-like separated, the space-like separation in quantum field theory is encapsulated by this microcausality, as it were, namely the subalgebras defined on the two respective regions. All the operators defined on the respective subalgebras must commute. However, Sorkin cleverly devised this idea of having an intermediate extended region that partly overlap with the future of S and with the past of R, and by carrying and he has a protocol such that you have an action that you perform on S, usually it's called the kick operator, is a unitary you perform in the subalgebra of S. Then M performs a non-selective measurement, so a measurement that you carried out without looking at the outcomes. So you just do the measurement, but you don't select on an outcome. And then R can do can measure actually the expectation value of a certain observable of an operator in their subalgebra, and it can detect the action of S by having this intermediate measurement. So, and this was called by Sorkin impossible measurements because two regions that are in which microcausality is imposed in space-like separation should not, under any circumstances, it should not be that there is the possibility through a measurement to somehow connect them, and so this leads to superluminal signaling in QFT. All right. So this his conclusion: these theoretically acceptable measurements must be impossible. This was somehow neglected for some time, and recently it had a new boost of interest, especially thanks to new works in quantum field theory, especially the Werk-fused mechanism of measurement. So quantum field theory is to date lacking a complete theory, consistent complete theory of measurement, and it's only recently that mostly from algebraic quantum field theory they have started developing one. And the Fuster-Werk mechanism is such a solution to how to perform measurements in QFT. But I will show that somehow it's still perhaps lacking something. So not necessarily that they cannot do it, but they haven't done it. All right. So the first thing that we have done is to study this problem in a more abstract sense. So forgetting about the space-time structure that comes from the relativistic part of QFT, and taking the non-relativistic limit. So you just you send the velocity to a very small one with respect to c, and these light cones just open up and everything gets aligned. So imagine that this is the same scenario where you have a sender, receiver. You have some local operation, also you can do in form of unitary, also some local operation in form of a local measurement. And in the middle, you have a certain region M, which is the one that we're going to study. Now, these two that I put here as communication, as compared to the one before, these clearly are not the problematic part of the story, right? Because this part of the region and these overlap causally, so they can actually have communication. So these can be directly substituted by something that can travel here. What we wanted to do is to study, therefore, the problematic part that clearly lies in this extended region in the middle, where you can perform certain kind of theoretical accepted measurements. And you want to do this without, so you want to see which measurements do not lead to signaling, or study how signaling is related to the possibility of performing these measurements. And yeah, so don't find offensive that I define no signaling and the following thing, the following statement that seems trivial perhaps in this community, but they have quantum field theory people and quantum information people have very different backgrounds and approaches, and sometimes the translation was not, in my interaction with them, the translation was not as straightforward as it may look like. So I want to remark the following. No signaling is a general abstract concept. No signaling is not related whatsoever per se to a space-time structure to relativity for sure. So no signaling is not related to the speed of light, is not related to the instantaneous speed of communication, is a concept that can be justified on many grounds. You can just take it as this formula of having the probabilities here with or without acting on another separated region changes the statistics, so changes the probability on the other side. This just, you can take it as, then you can try to physically justify why you would like to have no signaling. Of course, relativity imposes a very strong, we believe is a fundamental limit of nature that you cannot, massive objects cannot travel faster than light, so this is a physical justification of no signaling. But you can find other ones. So if you tell me that there is a 1 meter lead and concrete wall between two rooms, I still have good reasons to say that nothing is traveling from one room to the other, and I can think that this is a good justification for no signaling. So if you believe in information is a physical, is a something physical, as most of the time we believe in our works in quantum information. There is no information carrier that can travel from a region to another. This is an as good justification for no signaling than relativity. So I just want to disentangle this concept of relativity for no signaling. Okay, so let's study this problem. As I told you, the two extremal regions, sender and receiver, clearly are not the problematic ones since they can communicate to the middle region, both of them. So let's study what happens in the middle. Now, to model the fact that this region must be an extended one, the way we did it is to take the simplest model you can do. So there's smallest subsystems that can be separated, so you take 2 qubits. Classic. You have a qubit with a certain subregion A and a qubit with a certain local subregion B. So from now on, you forget that this is the mid. From now on, I will always consider exclusively what happens in this middle region that is separated with 2 parties that are the modeling of this extended region. And now we want to impose that these 2 cannot communicate, and you want to see which joint measurements can be performed on these two subsystems while keeping them separated. So you don't want to bring them together. And I will be more precise in a minute here. So which non-local measurements are no signaling in this kind of scenario that of 2 systems kept apart? And interestingly, these, for different reasons, from a completely different community, the school of Haranov, mostly Popescu, Weidmann, Grossman, studied such a problem without having anything to do with impossible measurements, without ever realizing that these 2 problems were very similar, if not exactly the same one. And so part of, I think, possibly the main contribution of this work I've done was really this translation of putting together rather unknown results, because these papers have very little citations at the end of the 90s, were not like very much, are not very much known in the community. So we have a bit rediscovered and developed further these ideas. And these ideas is how to measure non-local variables. So you have an operator that is defined over subsystems that are non-local in the sense of spatially separated. All right. So this is a dense, very dense slide, but follow me, it's an easy one. But so I want to first give a bit better definitions of what I mean. So from what is a measurement? What is a measurement? A measurement is a process that produces a piece of classical information, an outcome. And in particular, quantum measurement, I wanted to conform to the Born rule. I want the measurement to give me the same statistics given by the Born rule. Now, a first remark I want to make here is that the measurement ends when these pieces of classical information are created, even if they might not be available to any single local observer. I consider the quantum measurement finished when you produce something that can be written on a piece of paper. This is the same that, I mean, if you believe, if you have problem with this, you have problems with violations of Bell's inequalities. This is exactly what it happens, right? You claim that the measurement ends on one side and on the other side, and then later, only when you bring together the data, you can check that actually the violation happened. But why you are concerned with this? Because you believe that the outcomes were produced non-locally at different locations, and unless you're a cubist, this is, for instance, what cubists, how cubists solve the non-locality problem is that the measurement doesn't end until Alice, that is the only, let's say Alice is the only observer existing, walks towards what she believes to be Bob in her mind, and sees the notebook of Bob with, okay, this is just a digression, but if you don't believe in these very exotic scenarios, obviously you want the quantum measurements ends when they become classic. And the second part is that in standard quantum mechanics textbooks, the definition of measurement, so having a classical outcome in the form of an eigenvalue of the measurement operator with probability of the Born rule is conflated with the state update rule. Usually it comes in a single, mostly it comes in a single postulate, but this is not necessarily the case, that you re-prepare the states in an eigenstate of the observable, of the measurement observable. So I want also here to disentangle these two notions. For me, a measurement is only extracting the piece of classical information with the correct statistics. The re-preparation is a different problem. An ideal measurement is what I just said instead. So the measurement is ideal if it can be once performed immediately afterwards, it yields exactly the same outcome. And formally, this means that you have applied the Lüder's rule, the state update rule, according to that you have ended up in an eigenstate of the measurement. A joint measurement is self-explanatory, is a measurement performed on two or more subsystems. And a non-local measurement is a joint measurement where the subsystems cannot physically be brought together, or you don't want them to be brought together. Okay, so you want to have is a joint measurement such that the two subsystems, two or more subsystems, are not spatially brought in the same location. And again, this is not encapsulated by quantum formalism. This is something that you have to impose as an extra constraint, because the quantum formalism, if you only work in Hilbert space, once you have the tensor product structure, all the operators that are self-adjoint in that Hilbert space, no matter how this Hilbert space is partitioned, are allowed measurements. So you want, if the two qubits are exactly overlapping, or if the two qubits is one on Mars and one here, there is nothing in the Hilbert space that tells you this, so you have to add this as an extra constraint. And then I define a localizable measurement as a non-local measurement that can be carried out by quantum operations in these two local labs of the separated systems, such that the parties do not signal to each other. So this will be the main object of study in the reminder. So another note connected to this first one is that the quantum part of a measurement ends when you produce the piece of classical information. If the measurement is non-local, to know the result, it might require to bring the two pieces of classical information together. And I will show this. I mean, it seems a bit arbitrary here, but it's exactly how this will be done. So spoiler alert, non-local measurements can be localizable, but you will require additional resources. So you will need the entanglement as a resource to be able to localize these non-local measurements. And now I will go into that. Okay, so before explaining how to deal with the problem, let me first show you a more concrete example than the Sorkin problem was very abstract. This is like in the non-relativistic case, how you actually can do an impossible measurement. You want to measure these product twisted bases, where you have the 0, 0, 0, 1, but instead of the 1, 0, 1, 1, the qubit of Bob is rotated in the plus minus like this. These are orthogonal states, so they form a basis. Assume that the initial state, for instance, shared between Alice and Bob is the 0, 0. And now Alice can do nothing, in which case, so Bob is always measuring in the computational basis. Alice can decide to do nothing, and then Bob will always find the outcome 0 with probability 1. Alice instead can apply this kick operator in the form of flipping her local qubit. So she applies a sigma x kick operator. And in this case, the joint state gets updated to either 1 plus or 1 minus with probability 1/2. Therefore, Bob can find, with probability 1/2, finds the outcome 1 as well. So he can immediately detect by doing his local measurements whether Alice applied a unitary or not. And so this is signaling, and this is an impossible measurement in non-relativistic quantum mechanics. Now, following these works of, I want to point out that I have this amazing thing here. It took me a lot, so if you need the definitions to come back, they're here in every slide. So the localizable measurements how do you localize these local measurements? This is the idea following from Popescu, Weidmann, etc., etc. So you have this. This is psi I is the initial state shared by Alice and Bob, is the one that you want to perform the measurement, on which you want to perform the measurement. So they want to perform a measurement in a certain basis. You pick a certain basis. We will see that the choice of basis changes dramatically the amount of operations and the amount of resources you need to perform a local measurement. But anyways, the way it works is the following. So you have this local lab of Alice, this local lab of Bob, and they share a certain amount of entangled states as a resource. So they pre-share certain amount of entangled states. And then Alice and Bob can each perform a certain set of local operations, possibly on two or more of the qubits locally available to them. So they can apply some unitaries or do joint measurements, but this isn't problematic because they all have in their hands this bunch of qubits. And by doing these local measurements that can be complex sometimes, but just so local but joint measurements in general, they produce a certain amount of outcomes that we can collect into a single outcome A, and a certain amount of outcome that can be collected on B from the other side. And this concludes, as I told you, the quantum part of the measurement. Then A and B can be sent through classical communication to an external observer, and the observer can know the result of the measurement, and the result of the measurement is the correct one in that basis with the probability given by the Born rule. So without having to bring together, physically bring together this qubit here and this qubit here, that they are the one that you want to jointly measure, just doing local operations and joint measurements at the local level with the aid of additional entangled states as a resource, they can reconstruct the result of the measurement. They can carry out a protocol that gives you exactly the result of the quantum measurement you want. Yes?
Just quickly, so they only have one copy of psi. This is crucial here.
Yes. Yes. They only have.
Otherwise they could do tomorrow with.
No, they don't do exactly. They have one copy. So with a single copy, they can find always the correct result of the measurement. So the result of this measurement is a function of only the local results, small a and small b. Yeah.
But do you agree that no observer, except the O observer, knows the result of the measurement and could possibly then signal in the Sorkin setup to, I mean, the problem with the Sorkin setup, if somebody knows the result of the measurement before the classical communication is needed to go from A to B or from A and B to 0 to O.
But yeah, I understand. But for the Sorkin's measurement, you don't need to know the result of the measurement in between. It's enough. You do an operation without looking. You just move something. You magically perform a measurement behind your back, and this connects the two, the sender and the receiver. So it's a non-selective measurement in the Sorkin problem that you.
Yeah, I know, but
And also here, right? So here no one, they don't have to bring together any result. It's just enough that she applies something and Bob measures locally, and he gets immediately the.
what I want to say,
Yeah.
You somehow announced this. They could have done this. There is no problem. All right. So if they do that, they can do this. The Sorkin problem disappears.
Yes.
Okay, and they have done this at the moment of the measurement before the classical communication is sent. So there's no problem.
It doesn't signal this thing.
It doesn't signal.
Yeah, exactly. So that's the solution of the Sorkin problem. You can do this
I think the
because
problem
the.
with Sorkin is the assumption that this O, that receives the classical communication receives this somewhere before light crossing time. And that's
No.
Okay. I don't know.
Okay.
But we can discuss.
Maybe we can discuss later because maybe it's a bit long. Okay. Unless you're okay. Okay, so this is how abstractly you perform this measure. So there is two problems. Let me maybe clarify this. One problem is that, or there is multiple solutions to the Sorkin problem. Let me state it like this. One solution, which is the one in quantum field theory by Bornstein and others, they basically say, indeed, microcausality is not enough in general to say that you have no signaling between separated regions. It's not enough to have just commuting subalgebras. Therefore, you need further constraints. You need to somehow identify what kind of measurements lead to the signaling and rule them out from the theory. So you need like a rule that tells you like it's not enough to commute. What I'm showing here is that, first of all, these local operations here that are the quantum part of the operation does not lead to signaling in general. And if you wait later, you can also say that this was actually the correct measurements the measurement you wanted to do. So the part of the impossible measurement is before the communication, because if we believe that these results were created when the quantum becomes classical, even without knowing it, you would have had signaling. And then you can tell me, yeah, okay, you did something, but what did you do? I mean, you didn't perform the measurement I wanted to perform. And then I said, no, wait. If I bring the result together, I show you that I actually did this measurement. This is the.
My kind of understanding of the Sorkin problem, if this region in the middle
Yeah.
are extended in time to contain all,
Yes.
there would be no
Yeah, that's correct.
problems.
That's correct.
And so that tells me
Yeah.
that the hidden assumption, I don't think this is discussed in the literature, the hidden assumption is Sorkin problem, that the outcome of O is available in the restricted time region.
Okay. Well, I think it's a different solution of the problem.
The problematic ones are the ones that signal from A to B,
Yes.
and this one doesn't. Right?
Doesn't.
Yeah.
Exactly. And of course, I mean,
So if you would like to have a non-localizable, let's say, measurement, this would have to be like extended in time somehow. If you want to do that, and on top of that, not run into problems with Sorkin. But already these ones are not problematic.
these are not problematic, exactly. So you don't have to wait for the.
These are not problematic, in my view, because imagine there is no point in the space-time region, which is this parallelogram, without this kind of classical communication. I think that my intuition is that the problem arises because you say the result is available in this region.
But
this one
no,
is
I
already
don't.
not problematic.
Exactly. Without having to wait, it's already not problematic without waiting to know the result. Maybe we can discuss later because it's getting. Exactly. You do a quantum operation and immediately.
This is a local operation with classical communication, so problematic. Sometimes you are not allowed, for example,
Like a collective, a conditional measurement. If on.
A does something
Yeah.
and then B does something.
Well, which is this, by the way. Yeah.
Like Alice measured 0, measured this way.
Exactly.
One
Yeah.
measured the other way.
Yeah.
And this requires no communication.
But this is the non-localizable case.
Exactly. This is the localizable case. If you can localize them, you don't have to extend it in time. That's what I mean. But maybe we can really, unless you, yeah, I really,
You want to address the other ones?
no.
Sorry. Then I understand.
Yeah, that's why.
Okay.
So I addressed.
I understand.
Yeah. So okay. Let me go further, and then maybe we see if you're still unhappy later. Okay. So now I'm gonna show you a couple of these actual ways of localizing these measurements. So let's take again the twisted basis that I showed you before. That is a problematic one. If you just measure as you are expected to do, like with this kick operator on Alice, and Bob measures applying just the standard state update rule. Whereas here, let's do this scheme. So you have this initial shared state, and you have this protocol that Bob does a Bell state measurement, so a measurement who's in a basis, in the Bell basis, and produces an outcome B, which is 0 to 3, according to the 4 possible states that he finds. Alice independently, so they can be space-like separated if you want. So it can be arbitrarily close in time before or after what Bob does. Alice measures her first qubit in the Z basis and receives and produces an outcome A1. Whereas, and if she finds A1 to be 0, so this is a single qubit measurement, so it has only 2 outcomes, 0, 1. If she finds the 0, she measures the second one again in the Z basis, but if she finds the 1, then she measures the second qubit in the X basis, and she produces an outcome A2. Now, measuring A1 allows you to distinguish between this class and this class of states. Now, if she produces this A and this B, and you bring them together, you can deterministically reconstruct which was the outcome of the joint measurement. So the result of this joint measurement in this basis is just a function of BA1 and A2, like I showed you before. And there is no signaling. However, notice that the price to pay for this, so one of the price is a resource. In this case, it's a very small resource. It's just 1 additional EBIT. Another price, maybe a bit more high to pay, well, depends on taste, is that the measurement is not ideal. So if you redo it on the same state immediately afterwards, in this process, the local state of Bob gets erased. Therefore, if you try to reproduce immediately afterwards the same measurement with the same scheme, you don't obtain the same result. So is not an ideal measurement. Good. It was shown in these papers that a generalized twisted basis, where instead of rotating by 45 degrees plus minus, you rotate by an arbitrary angle alpha, but still this product basis. This is asymptotically localizable, meaning that for if you take n resource extra EBITs, extra entangled states as a resource, the probability of success of carrying out a measurement is 1 minus 1 over 2 to the n. But there are special cases. So for any rational multiple of pi, you have a finite amount of EBITs that you need. So if I showed you that if pi half, you need only one extra EBIT. For pi 4, you need 3 EBITs. For pi 8, you need 4 EBITs of resource, etc., etc. So this is already, this gives you a hint that there is a big class of localizable measurements, and it's not very special to be a localizable measurement with this scheme. I should perhaps mention also that almost all joint measurements, non-local measurements, are signaling. So it's not so the Sorkin problem is a serious problem. If you take it seriously, is a ubiquitous problem. It's not like that I showed you a very specific example that was tailored to show that there was signaling, like almost all. And this shows that there is a lot of localizable measurements, but I don't spoiler the end. Another localizable measurement, so let's go to something that is more perhaps interesting in the class of joint measurements that you can do. You want to do entangled measurements, right? The other ones, they were like still product. So you want to do entangled measurements. This has many applications also in network non-locality. It's an important topic in quantum information nowadays to have this kind of joint measurements whose eigenstates are entangled states. And the bell state measurement is, of course, the one that comes to the mind to I think everyone in the room. If I ask you what is an entangled joint measurements on 2 qubit, everybody would say bell state measurement. You can do entanglement swapping and teleportation with this. And how do you perform it in this localizable way? Again, you need only one extra EBIT as a resource, which is another bell state. And you do a bell state measurement on one side and a bell state measurement on the other side, receiving these 4 outcome, one outcome with 4 possibility and another outcome with 4 possibility on both sides. And here there is a simple trick, because it is known that the amount of phis and psis and the amount of plus and minus in a closed network of bell state measurements must be even. Okay, there is a simple calculation to be done. Anyways, oops. Again, by knowing the outcome A and the outcome B collected by an external observer, this gives you the correct result of the bell state measurement, just by performing 2 bell state measurements at the local level. Again, this is no signaling, but is not ideal. And there is this was a conjecture, but now has been formally proven that it's only the twisted basis and bell state measurement that are localizable by 1 EBIT as a resource. So it's only these 2 that you can, if you want to do a ranking of how difficult in terms of the resources is to localize a measurement, these 2 are the only 2 1 EBIT resource localizable measurements. Yes, yes, yeah, exactly. So the final results, which is not mine, is by Lev Weidman, but is that every non-local measurement is localizable given enough resources, so infinite resources. You can.
Sorry,
yeah.
Really still kind of angle. It's very nice. What
Yeah.
I want to say is that I distinguish the situation, even if we define measurement has been finished when the classical
Yeah.
data are there. In the space-time diagrams, it's very, it seems
Yeah.
to me very relevant where is classical data there. Because, I mean, if I need to convey no information, only if I have A and B together, otherwise I cannot convey information if I just have B or A. The fact that A and B are there, but not at the same place,
No, I understand
seems
this,
to
but
require communication between them in order then to communicate to somebody else. And that seems to me the source of the problem. In the algebraic quantum theory where they have the regions of space, if I understand this.
no, I understand, but I think that having, so I think this is an epistemic problem. I think that the outcomes are, since the 2 outcomes are classically locally produced, at that point, if there was a quantum operation that would lead to signaling, it's over what could lead to signaling. It's not the further classical communication. It's true that no observer in the universe can know the result of this non-local measurement until they meet later on. But if you believe, as I do, that the source is a quantum, as a quantum nature, the source of this impossible measurement is not clearly the classical communication afterwards that immediately transfers the signal on the other side. It must lie within the quantum operation what has conveyed this information. And if the quantum operation, I know probably you don't like this part, but but in the same sense of Bell's inequalities, right? What I was trying to explain before, like the Bell's inequalities are problematic, even if you need to know that they are violated, you have to meet later.
I think this is a different kind of problem. I agree
Okay.
with you with the value equalities. I agree with this, that's when it starts to be strange. And here it starts also to be strange. But I think not because the classical data are there, but because the classical data are assumed hiddenly that they are produced in the same restricted region, or let's put it in extreme case at the same point, which they are not.
Mm-hmm.
Or what is the conclusion that you then all the problems that are in the Sorkin problem can be realized in this way?
Yes. Let's get to the conclusions and then we. and then we discuss them. Okay, Bell state measurements, however, are very special. Bell state measurements are very special because imagine you have another, imagine you have a second EBIT as a resource. What you can do is, again, the same protocol I showed you with the two Bell state measurements, but then A is input as a kick here, as a unitary here. You apply a sigma A, a sigma B, depending on what you found here, and this phi state here gets re-prepared in the post-measurement state as you expect with a collapse with the state update rule. So up to a swap, then you swap back these and these here, up to a swap, Bell state measurement with two EBITs of resource can be performed ideally. So you can have this local set of operations that also re-prepare the correct post-measurement state, correct according to the state update rule. So according to what I defined as an ideal measurement. The intuition behind this is that Bell state measurements are locally already fully mixed, so they don't contain local information. And there is a theorem by Popescu and Weimar that all localizable ideal measurements must erase all local information. And since the Bell states are, by their very mathematical form, already not containing local information, is the only one that you can perform ideally with this localizable protocol. And indeed they are, so we can prove that there is they are the only joint entangled measurement on two qubits that can be performed ideally with this kind of schemes. Therefore, when I assumed before, I don't know if it was correct, but when I assumed before that everybody in the room, if I ask you to think of a joint measurement, you take Bell state measurement, we have to be a bit careful there because we are taking a state that is very, not only is maximally entangled, that separates it from other states, but if you want to rank these states with this localizability, you're taking really a unique exception. So perhaps Bell state measurements should not be used to develop intuition about joint measurements because you're like taking really an extremal singular point in the space of joint measurements. Okay, then there is there is not many well-defined joint measurements. There is this that Gizan and his crew have defined a few years ago in the context of network non-locality. For this triangular network, these are states that allow full network non-locality. Is a measurement. It's called they're usually called the elegant joint measurement (EJM). And they are the observable whose eigenstates are 4 partially entangled states, such that they're called elegant because they have a nice distribution, geometric shape in the reduced state in the block sphere. They are like the vertices of this regular tetrahedron in the two reductions in the block sphere. Yeah, so these are the states where M are these vectors pointing in the 4 vertices. And elegant joint measurements, we managed also to find a way to localize them using 3 entangled states as a resource. Here is a bit more complicated. You have first to apply a unitary of this form where the columns of the unitary are the 4 states of the 4 AGM of the basis. Then you do Bell state measurement between qubit 1 and 3 and between qubit 2 and 4, and you produce two outcomes with 4 values. Here you perform a Bell state measurement B, and based on what you find B, you apply on the second 2 qubits here one of the following operations, like this is sigma z, or sigma y, of Bell state measurements, but not along both along the z direction, but rotated Bell state measurement along a yz or zy plane. Anyways, it's a bunch of local operations, and again, collecting the outcome of this measurement, outcome of this measurement, outcome of these two best state measurements. Here I have skipped the classical communication, but you have again an external observer that can collect all these local outcomes and reconstruct univocally the result. Again, this is a non-ideal measurement. I mean, and I don't have to say it anymore because only best state measurement is the non-ideal measurement. And we have a conjecture that is almost proven that EGM is, yeah, it is almost, there is some twist, but okay. Is basically the only measurement with entangled eigenstates that can be localized with 3 bits and no less. So it seems to be somehow special also in this ranking of localizability resources. And I come to the general results of this whole business. So first, these are all proven theorems and lemmas, mostly in this collection of papers. Every localizable measurement must completely erase, as I told you, the local information about the pre-measurement state in order to be ideal. It follows the lemma that on 2 qubits, only best state measurements can be localizable. And on n qubits, GHZ-like measurements are localizable and ideal. So it's the extension of best state, is a trivial extension of the best state measurement for many parties. Second theorem, important theorem, all non-local measurements of any dimension of any number of parties are localizable given enough resources, possibly infinite. But there is another result, as I showed you, that there are localizable measurements that require only a finite amount of entangled resources, and also some of them very, very small resources, right? Like if I showed you the protocol with 1, with 2, with 3 EBITs, and yeah. So what's the take-home message of this thing? Is that given enough resources, impossible measurements are always localizable, therefore possible, but cannot in general be ideal. Yeah, just a short coming back to the original motivation for this work. You have like so how to read this? This is a series of communities. This is how they call the problem, and this is where they look for the solution. So QFT, the possible measurements. The solution is that they need a theory of measurement. The Haranov gang, they say contradicts causality, and they call that instantaneous verification, and some of these results. There is, maybe you know, this Gottesman, Presky, et al. Paper that is somewhat relevant, but I didn't discuss it. I was very confused at the beginning because it seems they have some conflicting results, but then we realized that for them a measurement is basically a many-word measurement, is a measurement that doesn't yield results. For them a measurement is just diagonalizing the density matrix in the basis of the measurement without looking at the results. This defines a measurement channel only if the measurement is ideal. It's not a measurement at all if the measurement is not ideal. Therefore, their results remain very partial and not very interesting for the impossible measurements. Yeah, so this is our suggestion to call these signaling measurements and which of them are localizable. And yeah, I think that it's important that these communities that are approaching such important topics from different angles should communicate more. And come to the conclusion that Sorkin's impossible measurements are a general problem of quantum physics and not necessarily related to QFT, as it has been mostly discussed so far in the literature. Impossible measurements we showed through some of our developments, mostly through the results of Weidmann, Popescu, etc., that are localizable. Hence, they are possible, but in general non-ideal. And there is really a very small subclass of them that can be ideally realized. So can we perhaps say that the projection postulate does not provide a good, or not even in general, a possible description of quantum measurements? And I remind you again that best state measurements is a unique exception, and you should not build your intuitions based on that for what concerns joint measurements. And after the conclusion, let me give you a few perhaps bold remarks. One bold remark is that this Fürsterberg mechanism is a very nice advancement in QFT, but still has done nothing. It has absolutely no, it hasn't described at all any possibility of joint measurements. It's only like a local coupling of a probe to a system, both of which are fields, quantum fields. But I think there is still a lot to be done there to check the consistency of this measurement scheme, to be able to reproduce at least the joint entangled measurement and how they deal with non-local measurements, and can they define a localizability of some sort in their formula. So I hope that this work connecting a bit these two communities can help them, can guide them a bit towards this direction of approach, trying to address these problems. I think that this contributes also in general to the understanding of joint measurements that remain very, as I told you, like most of us discuss only Bell state measurements, but there is infinitely, already for 2 qubits, there is an infinite class parameterized with 3 real parameters of joint measurements. And can this localizability help us defining classes or ranking them in order to single out certain interesting joint measurements in this jungle of infinitely many? Then there is an interesting point that I haven't made up my mind yet. So in possible measurements, we showed that is not a relativistic feature, you can have it non-relativistically. However, a new work by Moore and Ver, they take this Klein-Gordon field and they take the non-quantum limit. So they take the Poisson brackets of the Klein-Gordon field, and they show that already in this classical limit, classical not in this sense, non-quantum limit, and they show that they find some impossible measurements. So my conclusion was that this is a general feature of quantum mechanics, but they show that it's not even perhaps a quantum feature. So it would be good to study them at a more abstract level, maybe also with GPTs, and to see what are the basic ingredients for a theory to exhibit this kind of problematic behaviors. And these, okay, this is a bit maybe hard to follow, but in this property lattice approach, this kind of quantum logic, propositional logic approach to quantum mechanics, there is a theorem by Constantin Piron that shows that the covering law, which states that the projection of a pure state is necessary pure state, plus some other natural assumptions, then if you take this, the lattice of quantum property is isomorphic to the closed subspaces of linear space. So this is used from at least that approach of quantum logic to motivate why you should have linearity in the quantum formalism. However, we showed here that measurements cannot in general be ideal, so that the projection of a pure state is not necessarily a pure state, not always a pure state. Yeah, so this is just a bold remark that can this be a hint that when developing a full theory of measurement also for quantum field theory, perhaps linearity is not well justified, at least. It's not that it should be abandoned, but should be justified differently. Yeah, thank you very much.
Very nice problem. I'm going to abuse my function immediately. And then shut up.
Abuse.
Can you go back to the picture of the Sorkin problem? And now I would have a kind of a suggestion, maybe.
Yeah.
If we understand this M really as a 2 qubits extended, as you said,
yeah,
so that the first qubit is connected with S and the second qubit is connected with R.
Yes.
Can I use your examples and just assume that the result of both results are instantaneously available, because we say this is maybe not relevant. So I ask my question. So let's test that this is, that the mere fact that we have classical results at some instantaneous time to the second qubit immediately, would you have a signal or not? I don't know what's the answer. I feel like maybe you know the answer immediately or what?
So if you
so you
perform a measurement at Alice here,
and above whatever type you have with the entangled sources and
yeah,
whatever you want to make. In your protocol, eventually these results will be communicated classically to
yeah,
some O, but I don't do that. I
yeah,
say, no, this is not needed. I assume that immediately both results, as they are established as a classical data, are transferred to the position of the second qubit and can be communicated to R. And then I ask myself, is then S and R, can S in that way signal to R?
well, if Bob can receive the result of A instantaneously, yes.
But then this suggests to me it's not important whether they are established as classical, but whether established at the same point or later on. They have to communicate with each other. If we say that this is dangerous, what I said, then to me
okay, no, I understood.
it's really important to wait until the results communicate with each other.
No, actually, yeah, no, actually,
You don't think that
actually I don't know. Actually, no. I mean, I was thinking like if she communicates to Bob, Bob completes knows the measurement, but
I
it,
don't
yeah, you don't care if
I don't care about that.
I see.
Just communicate
I see.
between S and R.
I should think about it. I'm not sure now. Yeah, sorry.
No, yes, please.
So, okay, so thanks for a great talk. I was immediately thinking of the classical case, so it's interesting that you brought it also up in the conclusion slide. But here would be a classical intuition, and maybe you can tell me if the quantum case is substantially different. So I could think that everything is classical here. I have a bunch of classical bits, and some of them pertain to the space-time regions. And then in M, there are two bits on the left and on the right.
Yeah.
One possible measurement would be the parity of this. Like,
Yeah.
are they the same or are they different? Now, immediately it seems like certainly this pertains to this region, so I can think of doing this measurement inside this region. But when I think of that doing this instantaneously, then I would say, well, you know, if I know the parity on the right and communicate it directly to R, then this would be signaling. So this seems to be in the same way that Chaslov said. It seems to be tied to this thing that you imagine implicitly that the outcome is available on the whole region. So my question would be, is the classical case really very different from the quantum case, or what would you say about it?
Oh, I never thought about this. The only classical case I've seen is this very complicated QFT limit. The difference seems here that classically you don't expect this possibility of being so. The trick comes from the quantum formalism of this. You're tricked by the quantum formalism of thinking in Hilbert space structure. So once you define, or in subalgebras in this case of algebraic quantum field theory, which is even more abstract. And they say everything that lies in this subalgebra, I have a collection of operators defined in this subalgebra, that define my subalgebra. All of these operators, the self-adjoint ones, correspond to measurable quantities. And you don't differentiate what are the physically possible operations that you can do in this region. Whereas if you give me two coins and I have to tell the parity, I don't think anybody would say, like, without accessing both of them, I have to bring them together to so in this sense is like you don't have a formalist that allows you to measure everything that lies in this region. Classically, locality is more embedded in the classical measurement. That's how I see the difference. But if you assume that both are available in the whole region, I guess it's the same.
Yes, but it seems to me you could also be in the classical case be tricked into the same conclusion. If you like close your eyes and
Yeah.
you forget your intuition that you have about classical separation.
Yes.
Just from the formalism, so maybe this kind of tells you that you should say exactly what's happening if you divide it further up. So
Yeah.
motivates the study that you have. So, thank you.
Yeah, thank you. Yeah, it was very interesting to think about it.
It's really nice example.
Yeah, it was very nice.
Classically correlated coins, and then you locally measure parity and you find out what the It's
Yeah.
very similar.
Yeah, it's
to
very
the-
similar. Yeah. Yeah, it's a very nice example.
Okay, are there further questions? No. Wait a minute.
Yeah, no, just to try to explore a bit more this fourth point that you discussed, this connection with quantum logic. We know that every ortho-complemented lattice
Mm-hmm.
is represented precisely as you say, it's a unique representation.
Yeah.
This is not a sort of invitation to say that complementarity in QFT changes, in the sense that traditionally in quantum mechanics you have complementarity given by orthogonality.
Mm-hmm.
But in this case it's something different, no? And for instance, if I try to define some sort of a projective measurement or something like that in QFT, I'm facing this problem, no?
Yeah.
I'm facing this situation of that maybe complementarity, the definition that I'm using is not the right one for QFT.
I agree. I fully agree with this. Yeah. So I mean, that program is a bit abandoned, no? The quantum logic. But I think that some of these results could really be useful for once you are like redefining. You are opening the Pandora box or defining really the measurements in QFT. I think you should consider all these kind of problems that are like pointed out at from these quantum logic results. And I think that because this lattice is orthomodular, but it might require to redefine you cannot justify the covering law, and also perhaps complementarity should be redefined. I fully agree.
Any further question?
So it got a bit confused. So it looks like it is relevant where the classical information about the outcome is and whether it can be communicated instantaneously from Alice to Bob, or the ability for you to signal from S to R. It looks like it's, let's say, a sufficient condition. But is it the case that even if you do just like a normal projective measurement without knowing the answer, you can also signal?
A projective measurement, yeah.
It seems to be very relevant, but maybe not really the only.
Exactly. Because yeah, I think perhaps I mean I never thought about this, but I think that Chaslev's comments before are pointing a bit in this direction, that perhaps we should differentiate between kind of measurements that you can do in that region. Because if the measurements is really these non-selective measurements that you perform globally on this region without looking at it, then it doesn't seem relevant. But if you want to perform instead like the twisted Bezier showed to you, and you have exactly. If you have like these conditional measurements on one qubit, what you know, what is done on one qubit conditions the measurement on the other. In that sense,
I'm not sure. I see
yeah.
the global measurement also as a communication, but quantum communication, if you want. You can measure also locally with quantum states and then bring them together and make a global measurement. And then you need, again, light crossing time. I think it's really light crossing time. Communication, whether it's quantum classical between these two. And you can communicate by performing measurements. I mean, sometimes, depending on the initial state, you can communicate to other side by performing measurements, not selecting or anything like that. Like if the initial state is not totally mixed, you can do that. So even the choice, non-selective choice of the measurement can convey information. It's not
But-
clear to me. I mean, that's just saying it.
Well, but Charles, if you let's go back to this one. If you if I'm telling you I do something here, whatever, and I do something here, whatever, and these two whatever produce classical outcome, but whatever quantum whatever quantum operation I've performed do not lead to signaling from A to B, why the classical outcome would be the problematic part? Is clearly that you have to classically communicate it for them to be problematic.
Okay, I could imagine that this operation doesn't produce the signaling either on B or A,
Yes.
but nevertheless, and even knowing just A or just B, or sending this information, will not allow what was the RNS
Yeah.
to communicate. But I can think that knowing both on A and B can send some information from R to S. That's why I suggested to check this.
Yeah.
Because if this already produced input problems, I feel that really the distribution of classical data in the regions is relevant.
I understand.
It's not that
Yeah,
A and
but
B communicate. It's just
yeah.
the data that A and B taken together allow R to signal to S.
Yes.
Have it?
Yeah.
And I feel that that's the core of the problem. So
But then,
Happens with a projective
but
it
But-
will happen with
exactly what happens with a projective measurement. But here you constrain this in time if you want. Like you wanted to this be
Exactly.
constrained in
I
time.
think that
You wanted to have this constrained in time.
because they make
Okay.
the region, I don't understand algebraic quantum field theory, but when they draw the region, they restrict the time extension of the region, and then say, all summer measurements are impossible. Of course, they're impossible because you need more time to finish them.
Yeah.
If you extend the region, I guess they will not have any problems.
Yeah.
Like
But
this is something which I discussed with Maria. I don't know.
yeah,
Because for them a measurement is not the click of a detector. It's like there's an atom, a probe that interacts with something, and then in the very end there's a classical field.
yeah.
But they consider this measurement to happen when the probe kind of touched the atom or whatever.
Mhm. Everybody's free to leave that longer.
No, I just want, because I'm not very familiar with the fused protocol or whatever. And but as far as I understood, I mean, I think they showed that actually that's a question. So didn't they show that actually if you do properly algebraic quantum field and put some reasonable assumptions about some reasonable postulates to the theory, actually you don't get any impossible measurements. All of them are possible, right?
It's correct. But
So at least in their framework, they don't have a measurement theory per se, I believe. I'm not sure.
well,
But
they
show that there's no this signaling problem. Right?
they claim that that is a measurement. They claim that what I've done is the measurement theory of quantum field theory. And indeed, the way they did it, I mean, Chris doesn't agree with what I'm saying, but I think is developed to solve this problem, the framework. They say, no, it's just a contingency that it actually solves this. It's just a good measurement scheme. But I think is essentially this local coupling to the probe somehow immediately doesn't allow you to have this non-local measurement. They don't do joint measurements. They do only local measurements, and then in the region the probe must travel from here to here to have. So is trivially correct that you don't get these kind of problems, I think, in their scheme.
Yeah, but doesn't that follow from like very general assumptions like microcausality and that I always forget these things that the algebra should be completely determined by the algebra of if you have like these Cauchy surface
Mm-hmm.
and you have a region and you have a neighborhood of that region that determines the whole algebra of the causal diamonds, right?
Mm-hmm.
So, which seems very reasonable, and I think everything that they use are assumptions such like that, which, from the relativity point of view, would seem very natural, right? They don't impose anything which seems at least to be artificial.
I agree, but so far they're not able to address a series of interesting cases, such any joint measurement, and I don't know if nobody knows how difficult and how well this is described by the scheme. simple measurements of single systems is perfectly fine, and they don't lead to this kind of problems, and they are based on natural assumptions. But I would like to see them to be able to, for instance, describe how can you do these localizable non-local measurements in their scheme. Once I see if they claim that everything can be done with their scheme, just wait for it to be calculated. But I would like to see if, because perhaps there is often the case that you take a bunch of natural assumptions and then you find out that they're not good enough. So maybe their scheme is too restrictive than they think. But yeah.
Comment. I mean, they do it in the framework of what we call purification. So the measurement is an interaction with another quantum system. And then by start, because we are doing quantum field theory, this interaction is relatively relativistic.
Invariant, yeah. Covariance.
It's embedded that all what you can measure only the light crossing time. For the time that is a light crossing time from A to B. So, but by mere fact that the interaction is already taking care about how fast you can get some information from A to B. I think in that way, we go a little bit outside of the Sorkin region of one like that is the region, do this. They may then interact this and interact all about this region, and then of course they can do
It's a different notion of measurements.
different notion of measurement.
It's not a click of a detector, but it's an interaction.
Great, okay, good. Long discussion. Thank you very much.
Thank you very much.